Hello! So, in this video you might note not a thing written up there. That's because this isn't actually a video on a given theorem so much as I wanted to make a remark as it is technically stated in the book, but is actually hidden and not even well described if you find it. And this is a remark about something that's sort of taken for granted after a certain point in the book without being, as I said, sort of carefully mentioned. So after some point we decide that f is some Riemann integrable function, right, for f from a to b to r. So we claim that this implies f is bounded. So it is always the case, right, when we were doing properties and all that and really just marching forward, that we always keep assuming f is a bounded function, and then we talk about, you know, being in Riemann integrable and all of that stuff. But it turns out that this implication is true and is actually really important for a number of reasons. In fact, we use this in some of the various proofs and stuff that we do. But the reason why this is true, so let's say, let me just write sort of a pseudo proof here. By way of contradiction, suppose f is unbounded at, let's say, some c in a to b. I suppose I don't even need by way of contradiction. I'll do this as a contrapositive. So ignore the by way of contradiction. So suppose that f is unbounded at some c, and I want to conclude that f is not Riemann integrable. So let P be any partition. Keep doing that. So P is some x0, x1, xn. And denote denote an interval, let's say x I minus 1 to xi, that has c. So take whatever interval has c in it and denote it by the r. So basically I want to pull out the specific interval that has this unbounded point in it somewhere, right? And let me just maybe say it's unbounded at c, unbounded, let me just specify above. This will be just as true for below, but it'll make my life easier if I just pick one. So I'm going to say it's unbounded above, meaning that it's going to positive infinity instead of negative infinity. So if this is the case, consider u of pf. Well, what is this? This is the integral, the sum of k going from 0 to n of the mk minus xk minus xk minus 1. There we go. So in particular, this is, and I'm just doing this to really sort of hammer home what's happening, this is k equal to 0 with k not being that I, the one in particular that had c in it, to n, mk xk minus xk minus 1. So I have this thing. I can let's say I can do the sum for the upper sums everywhere except for the unbounded point, and let's just assume, which may not even be true, but let's assume for a second all of that works fine. I still have this I times xi minus xi minus 1, where this thing is that orth rectangle, right? But mi is supposed to be the max of f of x such that x is in this xi minus 1 to xi interval. To which I ask, well, what is that for that unbounded region? So the reason why we have to assume that f is bounded is because if f is not bounded at some point, that point has to land somewhere in one of these closed intervals, because these closed intervals cover everything. But if it's in one of these closed intervals, then the capital M, in the case of going to positive infinity, lowercase m if I were going to negative infinity, that thing, the max or the min, isn't defined there. And so U or L respectively, that piece just fails to exist, right? I can make some argument about trying to do some supremum, infimum, and maybe I include positive and negative infinity, but even that's going to become a nightmare, because then I'm going to start getting infinity minus 7 is my upper sum, and that's not a thing, right? So moreover, like I start getting really, let me just say, really bad things start happening at that point. And this is one of those things that you really struggle to deal with in other versions of integrating, like Lebesgue integration and Riemann-Stilch integration and stuff like that, is how do you deal with having these unbounded things? Now, to be clear, in fairness, there is sort of a subtype of unbounded integral that we can deal with Riemann integration when we get there, which will be soon. But we haven't got there yet, and that's called improper Riemann integration. So here, assuming we're trying to do proper, right, if f is a proper Riemann integrable function, meaning f is itself honestly Riemann integrable, then it must be a bounded function. If f is not a bounded function, there are clever ways of trying to figure out what would make sense as an integral, but that is not a thing we have covered yet, and even then it only works in sort of very somewhat specific circumstances. Okay, so I just want to make this remark. This is hidden at the end of a proof, and even then they don't really outline this part of it. They just make a point about the U and the L, and they don't sort of elevate it to this idea, even though they use this later. So I want to make sure that it's very clear that from this point on, or really from earlier than now on, we can make this assumption that if f is Riemann integrable, then f is indeed a bounded function. This is a part of being Riemann integrable, which you may not actually get with other forms of integration. So this is sort of specific to Riemann integration. Okay? And that is it.